Okay, my friends, this is going to be a day we're going to call it Closer to Home. And why is that? Because we're going to be looking at exactly how my odyssey in mud fossils began. I live in Middletown, Connecticut, which is just up the road from where Sleeping Giant is. And this is the history behind Sleeping Giant. And I think I can prove, well, not prove it, but I can show some of it has substance. Now, this is from 2006. They're saying on your ride to Quinnipiac College, it's hard to miss the mountainous region, also known as Sleeping Giant. Many have trekked the trails across from the campus, but few know the history behind the mountain. Dating back about 170 million years ago, volcanic eruptions formed the columnar patterns of basaltic rock called ridges. And I have some here, we're going to be looking at it, and I disagree with that. 170 million years, absolutely. And it says, in Connecticut, most of these ridges run from north to south, but one unique ridge, 6 miles north of New Haven, runs from east to west. It is this particular ridge that has the distinctive profile of a recumbent, lying down human. Now, Sleeping Giant Mountain has graced Quinnipiac College here with her beauty since 1929, when the university was founded. For years, students and faculty have enjoyed the Giant's ever-changing splendor. The scenery from the top of the mountain, magnificent now with the foliage. Meg Craver, a sophomore physician assistant from Dudley, Mass. Years ago, now listen to this, when Native Americans were resident to the area, these are the Quinnipiac Indians, they called the giant by the name Hobomock. Hobbomock referred to an evil spirit who became angry at the neglect of his people. He was in control of these people, apparently. He stamped his foot near the current location of Middletown, causing the Connecticut River to change course. And I've looked at that, and I think that very well could have happened. In response to Hobomock's damage, Keitan, a good spirit, cast a spell on Hobbomock, causing him to sleep forever. And then they quarried up there and did all this stuff. Well, during the quarrying, they opened that giant's chest up. Okay, that is Sleeping Giant, and that is Hobbomock. Now, the indigenous people that were here, the Quinnipiac Indian tribe, told the newcomers that that was Hobbomock, and they related that story. Now, virtually everybody in Connecticut knows about Sleeping Giant. You drive by, you can't miss it. Now, who would ever believe it was true? Nobody. And whoever would dig into this story about it, because it's obviously impossible, nobody did. So nobody does. Well, after I got sucked into what happened on my property, I realized this stuff is not out of the ballpark at all. And then I realized it's absolutely certain. And then I realized nobody could handle the truth. So let's see if you can. Okay, this is tendon. It's rock now, but at one time it was tendon. And here's the way tendons form. They're very, very strappy, really tough. And they come in these bundles of fibers. You can see how many fibers there are. That's what gives them their integrity. And they keep making smaller and smaller bundles. You see how this, one of these little squares here, or hexes or whatever you want to call them, turns into a bazillion other little hexes. These are the hexes right here, and they have a ton of these. And then that one will turn into a ton of those. And then you get down into the fibrils. The fibril attaches to a little tiny ball way down inside. Each one of those fibrils has a ball, and that ball anchors that sucker in there. You're never going to pull it out. Now, you see these different patterns. They say they can have 3 to whatever number of sizes. Well, the one I have right here, and I'm going to show you this in the microscope, and you're going to see it has a central core, and there is blood in it, just like there was the other one. And mine could very well be like one of these right here, one of these little squares. All right, the one they show in the columnar, in this one here, is not a square, as you can see. It's a hexagon, and a lot of them form in that hexagon, as you just saw that pattern. Now, let's see what this all looks like in a microscope. What the surface is, what this is, and then let's see if it will even respond to the catalase test. It might. Okay, so don't forget these statements. Columnar patterns of basaltic rock called ridges. Now, I have these in my property as well, and this is what they look like here. And they say they can have, most columns are hexagonal, but they may have anywhere from 3 to 7 sides. They can be like this. I have this here, and I have it all broken apart and looked at in my microscope. I know exactly what it is. I know exactly what that is. And that pattern right there, that circle pattern right there, is biological. That just didn't happen by accident. And mine has the same thing. And it's not just a formation of rock. And the surface skin around the outside is not just dirt. That is literally fascia and the membrane that surrounded that particular tendon. In this case, that's a tendon. In my case, I believe it could be a tendon, or it could be even a bone. But that, I'm pretty certain, is a tendon. They form in these columns, in these patterns, just exactly like that. I agree with that 100%. But it's not just volcanic. That is body tissue. Okay, let's take a Z-tour. We know we're talking about Hobomock. No question there. Now, he was in Middletown. Where am I? I am in Middletown. What did I find? I found this giant fingertip. And a ton of, I have all kinds of parts. They're just everywhere. Littered literally everywhere. And this is almost flawless. There's the fingernail. All right, that's the fingernail. That is a little pad that bumps up to the next bone. These are the 2 blood supplies. I broke this piece off over here to get down into where the blood is so that I could get a DNA test, and I did. And when I broke this off, you'll see that it was fingerprints. Whoops. Hold on one second. All right, this is, I believe, is a piece of tendon, and that is the core, and then all in here would have been little tiny fibrils. You see up here, they have a core, they have all these tiny fibrils, and at the very end they anchor with little balls at the end of these little tiny straps. Okay, just a quick shot. You can go back and look at it if you want. That's a cross section of a tendon. Alright, this is kind of unbelievable, but this is the back of my property right here. And they're building a house up here. I owned this property and I sold it off. And this is about a 50-foot drop from there down to where my house is. And then it's 100 feet down to where the road is. I think this is his head, and I think this is his chest. Now let's come out of this. Okay, let's come down here. Where are we? Alright, this is my house right here. Alright, and this, from here down to the road, is about a 50-foot drop. Sort of, somewhere in that area. This is the house that they put in behind me. Alright, now, I like I say, I own this whole area, all through up here and all that, and I sold this spot off because, anyway, this area here is 50 feet higher than down here. I found that big, gigantic fingertip, if I showed you or not yet, right here. And this is still my property. I own all the way over to here and around, all the way down around here still. But it's, my fingertip is still like 5 feet into my property. I sold right from about here back in this area. But like I say, I think this head and this is the body, and the fingertip was found here. There's body parts all over here. I mean, literally everywhere. Literally everywhere. Down there's stone walls, you can't see them. But this was a field. And they cleared these fields, and they put the stone walls around the fields. And there's stone walls here, stone walls all the way down, stone walls all the way down the road. They're everywhere. And they're just laying there. All the stuff I found was laying basically on the stone walls. Now, I did have an addition put on my house, and they took all this stuff from where they dug up, but a very small addition and not deep. And they piled it in the woods here somewhere. And this is where I was gathering stones, and I found all these body parts. And then I started looking all over the property, and they were everywhere. Literally everywhere. I mean, everywhere. Every single rock I was picking up was a body part, if you know how to look at it. So that's how I got sucked into this whole thing. But they're everywhere. As far as I'm concerned, they're everywhere. And this is, like I say, what really upset me was when they started doing the construction. I don't know this guy, and I just sold him the property. And I could hear them out there smashing boulders all day long for months. They were digging up, I'm telling you, body parts. And they did the same thing on my property. I didn't realize it back then, but I just found one shard out there of a bone that they had smashed up. I'll show you. And I figured out how big it would be in circumference. And I figured it out, it would be about 4 feet in circumference. Now that's not huge, because you divide that by pi and you end up with about a foot and a little more. But you know, a bone this size is not bad size. Let me show you the ones they just found in Thailand. You see this? This is a femur discovered in Malaysia, 237 feet long. And I can attest to the fact that that is biologically exact. And I'm sure they could get some. Well, there's no question what it is. Now, what it's from, I don't know. But it certainly doesn't fit any of the stories that I've heard about things. 237 foot long femur? No, I haven't ever heard about that. Have you? All right, this brings up the point that I've made a million times, is that it's all about the area, the conditions that existed when they were entombed. All that stuff they scraped away from this bone was flesh. That thing died, and it had its flesh with it when it died. It turns into stone. It turns into iron, which is your blood and flesh and so forth, and all of those things turn into stone. And as I can show you, this is a bone. That's a bone, same as this one here. Same as that one. This is cartilage. This is the bone. Now it's basalt. There is one tiny little taste of bone left right there. And I'll show you that in my microscope when we get a little further into this. I may not do everything today. The microscope stuff we might have to do on a second video, because it's going to be running pretty long. But this is something that should be looked into. Now, I was watching that movie Troll yesterday. It's exactly right. Nobody can accept the truth. They locked that guy away in the woods. It's the same thing they did with me, but I don't care. I like my woods. Now, I told you they're smashing all those stones up out there. It was just killing me. I wanted to go out and say something. My wife said, no, leave him alone. It's his property. I said, yeah, you're right. But this is a bone. And you say, oh, no, that's a concrete pillar. No, that's what I thought at first. And then I realized that all these things they smashed up, they had to smash them up because they were too big. That's the center core of the bone. And they were doing the same thing back there. All there, boom, 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 all day long. And there's still some very big stones out there that I can see that they decided they were just too big. Now, if you follow out the curve of this, it ends up being about a 4-foot diameter. Now, that gives you to the center, let's see, I don't know, it's hard to tell, but you'd maybe 1.5 feet or so around. Certainly this is much bigger. So, whatever it is. But I figured out my guy, with his fingertip being 3 feet long, just the one fingertip was 3 feet long. I figured it should be about 160, 170 feet long, tall. And I don't know what kind of bone this is, but this is 4 feet in circumference, which might work out all right. And even this bone here, this bone might be part of this whole same operation somewhere, some little tiny bone in the body, an eardrum or something. Alright, here's the best spot we've got for biology right here. And I don't know how long this has been sitting out there after they smashed them up, but I bet you we're going to be able to see some very certain biology here. Let's take a look in the microscope. Well, yeah, let's take a quick look at this one, and then next time we'll do all of this stuff, because I got a ton of stuff to look at in a microscope. And it's going to take some time, and only the people that are interested in, you know, a little more depth are going to be interested in that. So let's just look at this to see if I can prove this is anatomical, and then we'll go on from there. Okay, that's where we're looking right now, down into that central core of the bone that I have here now. That, I believe, right there is a blood vessel. See the black here and this here? Now, one or the other should give us a catalase reaction, if there's anything left to it. You know, this thing's been sitting around a long time. That's the top one, and this one we get down a little closer to the bottom one, see it? You normally see this. They're close together. And this looks like it's a runoff, but if I'm gonna put a little boy, I can't even think of the name of it. Hydrogen peroxide, and see if we can get a catalase reaction out of these. Normally, you would if it was active. Now, before I do that, I don't know whether I should put the water on first or the catalase first. What do you think? All right, I'll go with you. We'll do the catalase first. Now, I'm not expecting a whole lot, because don't forget, now this was 40 years ago I had this house built. So this thing's been sitting out there for 40 years, I'm sure. Now, will we get any catalase reaction, which is a ton of bubbles? I'm seeing movement. Yep, here they come. See, I told you. You can see them bubbling around here? There's blood in there. That's all blood in here. And if I'm going to try to get real close. I got to take it out of its holder, because it's an odd shape here. Hold on. I'm going to go right down on top of it. You see the catalase? I'm telling you, that stuff lasts forever. You see that bubbling? That's on this gigantic bone. You see those bubbles? See them coming out of there? That's the reaction of catalase in the blood and in the membranes to the invasion of the excess of oxygen. So it divides the oxygen away and forces it to separate. Anywhere where there's blood, see? Or membranes, actually. Mostly it's membranes. This thing's loaded. That's because it was only broken apart 40 years ago. Some of this stuff's been sitting around probably close to 1,000 years, and still has enzymes in it. You see that? This baby's saturated with the high catalase. Now this is kind of interesting. Look, let's take a look and see what that looks like in the microscope. Okay, we're going to be looking up in the microscope at that bone inside one of that fractured areas. And this is one of these little cavities in the bone. And you have them all through the bones. And the blood passes through the red and the black blood. See the red and the black? They pass through these, they call them bone foramen, which are these holes in the bone. And because every single cell in your body has to be serviced with blood, so forth, quite regularly. Now, this is up, we're going to dig down deep. Okay, so now we're down deep. This, I believe, is the fibrin. That is the clotting fabric. And these are, I'll show you because I have another one here that I cleaned out and looked deep inside. And we'll probably look at this one. I'll put a little water on in a second. But let me back out of here. I have to do this kind of slowly. And you see now we're seeing a nice reddish looking blood up here. It's down here too, but it's everywhere. That's a body part. Now I'm going to put a little water on there, and then we'll come back to it in a second. All right, there's the water that's going on there. And let's see what we'll come back to. Now that's just water. That is not catalase. All right, but it's sinking in and being absorbed. We'll come back to this in a second. And then we should see some better colors too. I'm going to just zoom in and out of this bone cavity. Now let's go down inside and see that red blood and the dark blood, the black blood. This red is being fed by this hole. The black is being fed by this hole. You see it? I'll show you another one I have where the scab is still in there. This, I believe, is the fibrin. And this is also part of this. Now, I'm going to try to scrape that out of there. Let's see what happens. It might even still be flexible. No, it's not the case. It's not, well, it's not too bad. That is the fibrin that would be the clotting fiber. Let me show you one that was very pristine. This one, like I said, been at least 40 years sitting in the dryness outside. Okay, this is a bone that was had a fresh scab inside the bone, and once it was literally blood that came out after the bone came out of the mud. Because the mud to the bone is just like flesh. If it's, mud is nothing more than red flesh that is basically disintegrated. It's not destroyed. Now, that is where the scab was. Now we're going to have this one showing the scab removed from the fibrin. Remember I scraped that stuff I said was probably fibrin, and it probably was. It just hardened up. Now, this is after both of these things are missing, and I'm showing just the two blood vessels. And you see the red one goes off this way, the black one goes off this way. That's where they fed their blood up to the next bone. You have to have the blood moving through these different places in the body, and it's fed through arteries and veins. One of them is red and one of them is black. And that's what their holes are, which I just showed you in that gigantic thing. Okay, all these tendon fibrils and even bones as well, they have a central core, which they have a lot of blood in the center. Now I'm going to put a little bit of moisture on it, and then we're going to come back and look at it. But you can already see that's exactly the same thing as you have here, identical. Let it dry up a second. All right, you should be able to see this pattern around here. And it was laying on its side, maybe down this way or whatever, but the blood seemed to coagulate this way. The one that's in the picture there looks like it might have been standing straight up, and it just made a really nice circular pattern. But a lot of them will have sort of laying one way or the other, depend. This probably was like this when it died, and all that stuff ran down to the bottom. I have other ones, they come all different ways. But that is what this is, and that pattern right there is fascia, which is nothing more than a membrane that's coated that particular tendon fibril, just like that one. So we got a lot of work to do here, but geology is completely changed, 100% changed. This is not basalt. Feldspar is not just some rock. It is the coding of biology. It is the fabric of biology. Caesar here, my goose, is also coated with feldspar. His feathers are there. There's his feathers. You see the feather pattern? See the feathers in his head? And he died in a flood. flat like that. One side is flat. Almost all my stuff, totally like that. This was DNA tested, CAT scanned, everything. Died in a flood. See, it's flat like a pancake. And this is the same fabric as this, the same fabric as this, the same fabric as Caesar. Same fabric as this. It's all the same stuff. And it's because it's collagen. Collagen has some affinity to bond with aluminum silicates and create a impervious barrier to protect the contents. And then the contents turn to basalt, like that neck right there. You see the neck? You know, I got to be honest with you. My friend Pedro is hooked in with all of these high-tech companies because he was a vendor and worked with NASA and European Space Agency and all this stuff. And he always gets these crazy things that nobody else knows about. I would never know about this stuff. So Pedro, thank you, my brother. He just sent me this. I'm just ready to wrap this up. I think I even said that we're done. Well, we're not done. This is Intel. Intel. Talking about where to look for bones using dinosaur artificial intelligence. Well, let's take a look at this. And again, this is Intel software. Only my buddy Pedro commented, and then I commented for Pedro. Anyway, here goes. And this is, again, Fair Use Act. I haven't watched this yet. I just barely started into it. And they're going to be talking about looking for dinosaur bones. Now, I showed you bones are just inside of the flesh that when they take it off, they can find something that looks like a bone, but you don't have to go in there. You should be looking at the outside stuff first, in most cases. But anyway, let's see what they have to say. Artificial intelligence looking for bones. I say they should use it for looking for blood vessels and arteries and veins and fascia and membranes. But let's see what they have to say. Here we go. I'm not going to say a word because this is not my video. This is their video, and I am just using it for commentary. Here goes. Again, Fair Use Act. And I'm going to comment to them. I hope they will respond. I'd love to have it. Intel, I'd love to talk to them about this and show them how to get information on what I present.
Welcome to this episode of Bone Hunt, Discovering Dinosaurs with AI. I'm Bob Cheesebro. I'm a solution engineer and a technical evangelist supporting One API AI here at Intel Corporation. In the last episode, we talked about how you can recognize dinosaur bones, but you won't have much success finding them unless you look for them in the right place. Fortunately, there are ways that you can determine where the specific places that may net you the most success. One way is to use a geologic map that shows the strata and whether the rocks are igneous or sedimentary. We look for dinosaur bones in the sedimentary rocks of the correct geologic age, and we use a geologic map to isolate whether they're Triassic, Jurassic, or Cretaceous periods. Triassic was the earliest, the Jurassic was the middle, and the Cretaceous was at the end of the dinosaur era. For this series, we are mainly focused on the Jurassic period, somewhere between 155 million to 145 million years ago, because of the prolific dinosaur bone beds from that period. The geologic features that we are looking at from this time is called the Morrison Formation. The Morrison Formation features many members within it. There are different members depending on their location. For example, in the southwest area of the United States, there are 3 members of the Morrison Formation exposed in New Mexico, where I am located. First is the Tidwell member, followed by the Salt Wash, and then finally by the Brushy Basin. The first thing you need to do is consult a geologic map to look for the Morrison Formation. If you break the Morrison into more specific units, look for the Brushy Basin member, which is a real juicy target. In the timeline, the Brushy Basin is roughly a 10 million year time frame between 145 million to 155 million years ago, according to geologists. Before we go on, here's a little paleontology history. The famous dinosaur bone wars from Othniel Marsh and Edward Brinker Coate took place in New Mexico, Utah, and specifically an area called Como Bluffs, which is located in Colorado. During their rivalry, they would destroy each other's finds as they were racing to get their own finds back to museums in the East. They initially struggled with each other intellectually on papers, but soon their rivalry escalated and got nasty, destroying bone sites and stealing things. Eventually, it brought both men into a little bit of ruin. The Brushy Basin is part of the Como Bluffs makeup, where much of this conflict occurred. The Brushy Basin member can be found all over the western United States, and this map shows where the outcrops of the Brushy Basin are exposed. The types of soil and context can and will impact the success of your hunts. The members of the Morrison Formation are what we call alluvial deposits or river-deposited sediments. Sometimes those deposits occurred in slower moving areas with more clay, like a marshy, muddy area. And then there were river channels that would go through there as well. The river channels carried larger pebbles. These rivers were typically closer to the mountain ranges in the southwest area. These rivers drain from the mountains down towards a seaway in the northeast or into a lake. These rivers were pretty energetic, and you can see the energy evidenced in the types of rock. In many cases, the rocks have larger cobbles, clasts, and pebbles in them. These are the areas where dinosaurs came to the water to drink, and many potentially lived near these rivers. So when they would die, they would occasionally fossilize in those rivers. Some of their bones may have been decayed, or perhaps a scavenger would pick at them, but some bones would get washed down the river where they would be deposited into sandstone beds and those larger cobbles and pebbles in that energetic area, and that's where we find a lot of bones. Bentonite clay areas from a unique situation because the clays are often different colors. What we see nowadays after it's been exposed is a variegated color of grays, pinks, purples, and olive greens, typical of bentonite clays. Then typically the sandstones would be yellow tones, yellow-green or orange in color, and sometimes just in the interface between the bentonite clays and sandstones, we find dinosaur bones. Often these sandstone beds are formed on top of the bentonite clay, which is very soft and will wash away. So the sandstone on the clay is like a birthday cake sitting on top of Neapolitan ice cream on a hot day. As the ice cream melts, the cake is no longer supported by anything solid and will break into pieces and chunks. So that's similar to sandstone, which also breaks away in chunks. The patterns of boulders and chunks, the variegated coloring pattern and the color and texture patterns are what we are trying to identify, because that's where you tend to find the bones. The AI solution we developed is designed to try to find those patterns and textures that are being exposed through erosion. Now that we know where to look, we can progress towards labeling, feature engineering, and other AI tasks. That's all for this episode of Bone Hunt, Discovering Dinosaurs Using AI. You can find links to resources, tools, and downloads, as well as where to learn more about everything in this series in the description. Remember to like and share this video and subscribe to the Intel Software YouTube channel. We'll discuss data collection, training, and cleaning in the next episode as we continue our dinosaur hunting adventure.
Boy, would I love to be able to engage, my friend. And the things I have are just nobody's ever expected. So there's no belittling anybody or trying to act superior about it. I just fell into this. It was just an accident. But I'm having a hard time finding anybody to engage, which is very distressing because I put a lot of work into this. So people that are making these claims, I'm certainly hoping will engage, and so far I haven't had that. However, Intel, I would think they're going to hold up their reputation as being, scientific people, science. I don't see that in the academia world now, but hopefully in the scientific realm, Intel will engage. That's all I can hope for. And I really, really want to engage. All right? Thank you all, and stay tuned because this is going to get very, very, very deep. Boy, I was just looking up Bob's page here. This is Bob Cheeseborough, the one from Intel, and he's talking about hunting dinosaur bones and all this stuff. And nobody's ever expected what I had discovered. So I'm not pointing any fingers at anybody. I just want to engage. And, I have some other ideas Intel may be interested in as well. But to be able to talk to Bob, Well, I'd love it, my friend. I am going to try to contact you and see if we can compare notes. That's all I'm asking. That's all I'm asking. All right? Happy New Year, everybody. I love you all.